Hello and welcome to RF Design tutorial. This is tutorial 17 on Practical Power Amplifier Design. This is part 2 of the video talking about different steps we needed to take to reach from device level to final layout for a 10-watt Practical Power Amplifier design. That design we will validate for one tone, two tone, as well as modulated signal analysis, and then finally performing the DPD to linearize the power amplifier. Now, before we start, subscribe to my channel. Once you subscribe, click on the bell icon to enable all the notifications. And after you watch the video, don't forget to give it a thumbs up and share it with your friends and colleagues who may be interested in watching similar tutorial. All right, so let's quickly recap what we did in part 1 of this video. We learned about the basics of PA design, and we went through series of topics till we reached to the point where we have a good source and load impedance points for performing our matching network. In this part of the video, we will finalize the PA design by doing the matching network design for input and output stage as required. And then we will finally optimize the PA for fundamental and harmonic performance, and then perform two-tone validation to note the IMD products. And finally, we are going to talk about how do we go about preparing a layout for power amplifier and then performing EM circuit co-simulation for the final level validation. In part 3 video, which will be the next video in this series, we will look at modulation analysis and also performing DPD for our design. Now, before you watch this particular video, I would recommend you to go ahead and watch tutorial 16 because this is all in sequence. So if you don't watch that video, you will miss some of the context we are going to talk about in the present video. Now, quickly, just to remind you what goals or what specifications we are designing for is a 2.4 gigahertz amplifier with plus minus 100 megahertz bandwidth, 10-watt output power, and better than 50% power added efficiency. And the device which we are using is one of the Cree device CGH40010. All right, so let's directly dive in and look at what point we left in the last video. So here in last video, we did the validation of the source and load impedance, which we obtained by performing couple of load pull analysis, and we validated our bench and we finalized this is going to be our source impedance and that's going to be our load impedance which we have to match. Sorry for the typos. So this one is 28 plus j.5. So that's the impedance target we have in mind, and that's what we are going to go ahead and do the impedance matching network for. All right, so when it comes to matching network in power amplifier, I personally prefer tackling the output matching first. Now, once we have our goal set, how do we go about designing a matching network for something like a power amplifier circuit? Now, in ADS, as I talked about in some of the earlier videos, you do have different techniques of doing impedance matching. You could use a Smith chart utility, or you could use impedance matching utility to synthesize your matching network. And we already have discussed this in the previous tutorials. However, for power amplifier output matching side, the traditional way of doing impedance matching may not give you the desired results very quickly. So here is the technique which I would recommend you guys to use. Although decision is yours, you can do whichever way you want. The way we approach this matching network is by setting the frequency, which is typically the center frequency in our case. And based on all the analysis we have performed in terms of load pull and other simulation, we we define certain variables. Like in this case, you can see I have defined Z1 real, Z1 imaginary. So that's the impedance real and imaginary part, which I'm looking to achieve over fundamental. Z2 real and imaginary is our second harmonic specification. And as you can see, I would like to short circuit in the second harmonic. And my matching network should produce a short circuit when it comes to the second harmonic frequency. Similarly, in the third harmonic frequency, I also would like to have a short circuit and the Z4, which is actually the fourth harmonic, I'm only optimizing the imaginary part. Now, once we declare these variables, how do we go about preparing a matching network? So here is a representative circuit which I believe can do my job, and I come up with this simple T junction, and that's my drain bias line. Remember, in power amplifiers, in a normal amplifier, I talked about having a high impedance lambda by 4 line. But in power amplifiers, this is the drain line, and drain current would be much higher. So it's difficult to maintain a high impedance line because the width of the line will be small, and you are going to draw a large current to the drain terminal. So in this case, I have decided to keep it as 50 ohm, which give me wide enough line to allow for that kind of drain and the temperature rise, which will happen due to the higher drain current. So I'm going to keep it 50 ohm. I'm not going to optimize that. But rest of the transmission line, which are certain representative, and you can start with any number which you deem suitable as a starting point. But because I use this kind of network time and again, so I have copy pasted one of the matching network which worked in my other design, and here I have defined the impedance to be optimizable from 20 ohm, and now we will go till 90 ohm. If you remember, in one of the earlier matching network topic, we discussed this is typically the most practical impedances which you can achieve over a microstrip. So we would not like to extend anything which is unrealistic at the end of the day. And these are ideal transmission lines not yet converted to a physical microstrip line over the dielectric which I'm going to use. And the electrical length, well, you have more flexibility in coming up with the length which is suitable for your kind of matching network. So similarly, I also have a series capacitor which is going to be acting as a coupling capacitor. And here you can notice I have a couple of steps. So the first step here is the short circuit step. This, these two steps will help us to achieve the harmonic performance which we are looking at. So this step is going to provide the required harmonic rejection. And once we run optimization, the impedance and the length of this step will be calculated. Now all these transmission lines, because they are ideal currently, the impedance and the electrical length is being calculated at a certain frequency. And this variable I have set to my center frequency, which is 2.4 gigahertz at the moment. Now, once I have this representative circuit where I have a 50 ohm termination or resistor at the end, and then I have a 50 ohm termination at the input. So all the impedances which we are going to look at is with reference to 50 ohm, and this will be the target which we would like to achieve from our matching network. So that's the representation and the variable. Now, how do I set my analysis? Well, in a normal impedance matching network design, you can set up one single sweep of S parameter covering the entire frequency range. But here, remember, we have a specific targets to meet at a specific frequency. So this is how I would recommend to set the S parameter and then eventually use that in our optimization. So the first S parameter controller here is only doing a single point analysis at a frequency of f, which is 2.4 gigahertz. Now at that frequency, I would like to achieve these two goals. One, which is the real part of Z parameter computed from S11 of our matching network. So here I'm simply using a function S to Z and passing in S11, which will be produced by S parameter. And I would like that S11 or Z11 to be equal to the variable which we define using Z1 real. And in the other side, we have the imaginary term, which will be equaling to this Z1 imaginary. So essentially, we are setting a goal to come up with 28 plus J 0.5 ohm at the fundamental frequency. Similarly, there are other goals. So this is parameter analysis will be run on a single frequency, which is 2 times the fundamental, which is second harmonic. And I have given a zone in order to reach to the point which I'm looking at. And in this case, it's a short circuit. So as long as I'm near about short circuit, that would be acceptable. And I have some min and max limit defined. Same thing for the third harmonic, which is going to be computed by 3F. And finally, the fourth harmonic, which is again only optimizing the imaginary part. Now, once we have these things in place, everything is optimizable. I have set an optimization controller here. And currently, I'm starting with gradient. You could use any kind of optimization type you want to use, and we can give it an optimization run. And now you can see at various levels, we have the goal for the real and the imaginary part for fundamental as well as second and third harmonic. Now, after we kind of reach very close to our goal, you can see the error function is e raised to minus 6, and the optimizer is commenting that there's no further improvement possible. So this is the best possible case. Now, while that happens, if we look at the data display which we obtained, in this data display, I have plotted 3 targets. So this is what we set in our schematic: Z1 target, Z2, and Z3. And then the S parameter which we are obtaining at different frequencies. So targets are denoted by these circles, and our circuit response is denoted by this cross. So you can see at fundamental, we are able to achieve the impedance which we wanted to, and as well as we are very close to what we wanted to achieve in terms of harmonics. So all in all, this matching network is giving me the desired response, which I'm looking at to match my power amplifier. Now, if you want, go ahead and update the design, and you can simulate the design once to verify everything is okay. Now, because I keep this schematic for tutorials, I will not go ahead and update the design. But in reality, I have updated the design so that I obtain the right values for these transmission lines or capacitors as you might have used. Now, once I have the matched the impedance matching network design already done for the output side, I'm going to simply use this subnetwork, and if I push down internally, you can see this is the optimized values of all the transmission lines which I was looking to achieve from the matching network. So instead of terminating the output to 28 plus J5, I turned it back to 50 ohm because this matching network is transforming that impedance. And this is my drain supply, which is going through this particular terminal towards the device. And I have a couple of bypass capacitors mounted there. All right, at the input side, I'm terminating the device into the most optimum source impedance, which we found using the load pull analysis, which is declared here. Now, if this matching network has done its job, if I go ahead and run this analysis now, I should be able to see the output power level, which I was hoping for, and the efficiency level should be good because these parameters were extracted from the load pull analysis, which essentially is the case as you can see here. Also, because of the impedance matching, you can see I have obtained a decent looking gain and the return loss which I was expecting. Now, still it is not as optimum as I would like to do. So we can go at a second level of optimization. And here I have defined the goals slightly differently than what we used during the matching network design. So here the first goal I have is a power delivered, and I would like to achieve greater than 41 dBm of power. Then at the second harmonic, you can notice this V load, that's the node name at the output, with this capital bracket, and then you have 2, which is second harmonic at V load, and I would like to achieve that no more than 0 dBm. So output power, I'm expecting to achieve is 41 dBm and the second harmonic is 0 dBm. So that gives me greater than 40 dB of rejection. Similarly, the third harmonic at V load is going to be, my target would be 0 dBm, and then DBS22, which is the output reflection, based matching. I would like to achieve better than minus 20 dB in the frequency range of 2.3 gigahertz to 2.5 gigahertz, because we are dealing with plus minus 100 megahertz of bandwidth. Right, so once everything is set, this matching network is already optimizable. Input matching network is not designed yet, and that's why we have terminated that with the optimum impedance. And now we can go ahead and optimize this matching network based on the harmonic balance response. And now if you see this purple curve, from 2.4 to 2.3 to 2.5 gigahertz, we are able to achieve better than 20 dB return loss. The output power is as expected, more than 41 dBm, and the second, third, and the harmonic is 0 dBm or below. So now your PA is being analyzed using this optimized condition. And again, once we update the schematic, we will have the right values. And again, remember, just to reiterate the point, all the optimization variables we have used, keeping in mind the practical limits over which we can, achieve with the transmission line components. So we are not inviting any surprise, because tomorrow you should not see, after putting in a lot of effort, you perform optimization and you end up getting 10 ohm or 5 ohm of line, or maybe 200 ohm line, which is very difficult to implement in real PCB using any kind of practical dielectric like Rogers material or anything. So we have taken care by setting those constraints appropriately. Now, once that is done, we have completed the ideal output power matching network design and optimized our PA for nonlinear performance. So let me close some of these windows which are open. Now, what is the next step? Of course, next step is to perform the input matching network. Now, for input matching network, you could use a traditional Smith chart based approach, because the source impedance is going to be 50 ohm. The input impedance which you have to match for this PA is 6.7 um, minus some J value. So that can be set in the Smith chart tool. And if you go inside, basically it's a double step kind of matching network, which I have designed. And again, all these things I have already covered in a very detailed manner in the impedance matching videos. So there's no major, technique which you need to employ on the input side. But in case, depending on your power amplifier design, if you also want to achieve a certain criteria in terms of harmonic terminations for the input side, the same strategy which we used for output matching network, you can also employ on the input side. But in my case, that was not necessary. So if I go inside this input match ideal subcircuit, basically it's the same network which I just showed you using the Smith chart tool. The only difference here is I have added a high impedance lambda by 4 line for the input bias, and this is the point my DC bias will get fed. Now, because the gate current is not going to be as high as drain current, so I can take liberty of high impedance line, which is basically going to be a thinner line when we implement it on the PCB. So with these two things, I have a full PA design with input and output matching network, and the source and load termination turned back to 50-50 ohm now, because we are no longer needing to terminate it by ZL or ZS as conjugate or a complex matching. That job or that transformation is being provided by this matching network. And again, keeping some practical things in mind, I have added a 50 ohm line here, because remember, when you finally assemble this, you will need a line to place the lead of the drain. So I have connected a 50 ohm line with certain small electrical length at both at the gate and the drain. And for this resistor to get mounted, I have included a small line. So keeping how eventually you want to prepare the layout is always going to help you. And once I had introduced these lines, once I introduce the input matching network along with the output matching network, things might change a little bit again. For example, if we go and perform this analysis here, you can see power is still more than 40 dBm. The harmonic performance is pretty good, but the output matching got disturbed because of the inclusion of input matching network, which is not providing exactly the impedance which you're looking for. And also the input matching network is showing a certain frequency shift. And again, at this point, we can go ahead and use the same optimization bench which we had earlier. All right, so we can go ahead and optimize this design again to balance both input and output matching networks. So here you can see I'm trying to meet the DBS22 target. I'm trying to meet the DBS11 target along with the harmonic power and the fundamental power. And I'm pretty close to meeting the required error function to meet my goal. And we are almost there, except a minor written loss kind of variation. So if we keep on running in next few seconds, I will meet the required target which I have. And as you can see, I'm pretty close. So at this point, I can stop the optimization just for the sake of time. I can go ahead, close and update the design. And once we update the design, we can just simulate it once with the refreshed values. And now you can see with both input and output matching network, my efficiency is around 66%. Output power is 41 dBm or above 41 dBm, kind of flat gain in the frequency band I'm looking at. Both input and output matching network is pretty good because the return loss is much better. All right, so at this point, we have the working PA with all the transmission lines and the capacitor models, etc. What's our next step? Well, the next step obviously is to convert these ideal matching networks into practical matching network, or converted with reference to the dielectric which you are going to use. So that step again I have already covered in one of the impedance matching networks video. And here if I push inside, I'm going to use Rogers 4350 substrate, and I'm going to use 25 mil, and these are the specification. And I'm going to use 2 ounce copper just because it's a PA. So having a little bit thicker metal will always help me because it's a 10 watt kind of device. Now again, using the techniques which I also talked about during the LNA design video and other impedance matching videos, I have converted all the ideal transmission lines into the practical transmission lines with all discontinuity models taken into account. For capacitors, I'm also preparing the mounting pad to take care of those parasitics which may be caused. So this is the how output matching networks looks like. In input matching networks, my apologies. So on the output matching network side, you would notice this is slightly different because when I was preparing the output matching network, I converted everything to transmission lines. And then when I optimized my design, the overall PA design, let me activate this line. You notice I ended up getting a pretty long transmission line, which is 29 mm, but the width was bigger. So that means that line was producing a capacitive action. Now to save some space on my layout, to avoid this kind of long transmission line and a wide long transmission line, I simply replace that transmission line by a capacitor. Because 2.4 gigahertz kind of frequency, it's pretty easy to get the capacitors at a pretty high Q value. So instead of using transmission line in my matching network, I simply replaced that by a capacitor, and then I performed optimization to come up with the right capacitance value. So that's the trick I use to squeeze the size of the layout as much as possible. Similarly, the other transmission line, which was there in my original matching network, after optimization, I found out it's going to be around 19 mm. And again, this is like a big transmission line. And that also I replaced with a capacitor. So after these two changes, rest of the network remains the same. So here is your 50 ohm line, which is close to 90° or lambda by 4, slightly lesser than that, and rest of the transmission line already taken care of. So these are some tricks which you could use practically. If you have a very high impedance, it's very easy for the transmission line. I can create a meander line. I can fold that line to squeeze the size of the PCB. But if you end up getting a wide line, which is quite big, no matter how much you do, you can still not, cannot squeeze it enough to come up with as compact PCB as possible. All right, with these two changes, I have the input output matching converted to full transmission line. The same optimization goals were used for optimization. Now, because I have both input and output matching network, I added a goal to take care of S11 better than minus 18 dB in the frequency band we are looking for. And also the large signal gain, which we were computing using these equations here. I have set that goal because I would like to achieve at least 12 dB of large signal gain. With all these things, I went ahead and performed optimization of my design. And here is the optimized response for the PA. Again, we are meeting all the targets, but in case you think some of the harmonic levels are higher than what you're expecting, and if you tweak anything, you can feel free to go ahead and optimize the design again. And this time you are not optimizing impedance or the electrical length. You basically are optimizing the physical width and the physical length of these transmission line. And again, in few seconds, I would be able to fine tune my matching network again to give me the right harmonic performance, the fundamental performance, as well as the gain and the matching performance as we are requiring. And you can see now we are pretty close to achieving the error function of 0, meeting all the goal. We are mainly only missing on the gain part. So our target was 12 dB, and currently we are around 11.9 dB, which is kind of good enough. So if I want, I could stop the optimization right now, and then I can go ahead and update my design. And after I update my design, I can just go ahead and give it a final simulation run. And now you can see your second and third harmonic performance pretty good. Impedance, the fundamental power is also pretty good. And then you have excellent impedance matching around 2.4 gigahertz, giving you better than 18 dB of return loss for both input and output. And the efficiency, the train efficiency, the large signal gain, everything is kind of meeting the specification which you are looking for. All right, so let's go back to the slide and look at where we are in terms of agenda. So we talked about doing ideal input and output matching network. We converted both input and output matching network to the microstrip configuration using Rogers 4350 material, or you could convert it as per your own material. We optimize the PA for performing fundamental and harmonic performance so that we have the right distortion levels in our design as per the specification. Now the next step is to perform the PA compression analysis and to capture the 1 dB or 3 dB compression point, and then performing a two-tone, and then we can proceed for the layout preparation and doing EM circuit core simulation. So let's talk about that in next few minutes. So once we have everything, let me close all the designs, and I'm not going to save anything here because I've been playing around with some of these values. All right, so step number 7 is to perform PA sweep. And again, it's very, very simple. As you know, I have a variable here, PAVS, which is available source power. In my harmonic balance, I'm going to define a sweep to sweep the input power level from 0 to 35 dBm at a 0.1 dB step. Essentially, we are going to perform 351 harmonic balance behind the scene. And then once we run this analysis, we would be able to plot the output power delivered versus input available source power, and also looking at the large signal gain versus input power. And here we are plotting the drain efficiency and power headed efficiency versus input power. And I have put some markers at certain locations. So let's talk about that. So the large signal gain on a nominal, design after we perform all the impedance matching, etc., is around 14 dB. Now, when we look at another marker which is placed at 11.2 dB gain, is the 3 dB compression point for this device or for this amplifier. And the input power level to achieve 3 dB compression is around 30.4 dBm. And similarly, you can place this marker to 1 dB compression point approximately somewhere here. And now you can see at 1 dB compression, you need to feed around 21.9 dBm of input power of that. And the corresponding, output power, you can also note here at 1 dB compression, what is going to be the output power which you need. And at 30.4 dBm input power, the output is around 41.6, which is 3 dB compressed. So approximately 11 dB of gain plus 3 dB compression. So you have around 14 dB of gain here. And at that 3 dB compression point, the power added efficiency is 63%. Remember, we were looking for achieving 50%. So we are getting much more than that. And the drain efficiency is around 68%, which is exactly what was also mentioned in the data sheet here about that. Right. So in this case, my swept performance of the PA is validated. We can go to the next step to set up a two-tone analysis for this PA. And again, I have separate videos on performing harmonic balance, one tone and two tone. So here I have connected an N-tone source with the center frequency minus some offset, center frequency plus some offset at a particular input power level. Now, whenever you're performing two-tone test, make sure your power is in the linear region. The input power is in the linear region, and that you can compute from this curve here. So typically, this is the region where you may want to run this two-tone test, because as soon as you start approaching compression region, your intermodulation distortion calculation is no longer valid as per the references. So I'm feeding 20 dBm of input power, and that means I would be somewhere closer to this zone here, which is definitely the linear operating point of this PA. All right, so in terms of harmonic balance, I already set up this condition here. So this is the input fundamental frequency, and the offset I'm using is 1 megahertz, but you could change the offset as per your requirement. And to compute the IP3 or TOI on the upper and lower side, I have placed these two measurement blocks. Remember, from the simulation HP library palette, we do have these measurements which we can place. And here I have used this IP3 out template, and I've entered the specification by specifying the node name at which we are measuring and then the harmonic order. So one measurement is for the lower side of IP3, another is for the upper side of IP3. And again, these fundamentals have already been discussed, so I don't want to spend too much time here. So once we perform simulation, we can plot the V load, and ideally when you plot the V load, originally, this is how you will end up seeing this spectrum. So let me go ahead and plot V load. So you will see spectrum around all the harmonic frequencies. Then you zoom in around the fundamental point by using this zoom icon. and you will need a couple of tries in order to zoom in, because the frequency spacing is too small, and then you would be able to see this kind of spectrum, and that's what we have plotted. So here is the marker for one of the tones, and this is the third order product which got generated, and you can see the delta. And here's the IP3 lower and IP3 upper. And our target was to have greater than 45 dB of IP3 or 45 dBm. And here we are able to achieve 47.6 dBm, which is beating the specification which we had for our PA here, right? So meeting the bandwidth requirement, we are meeting the output power requirement, gain, return loss, PAE, as well as the IP3. So all specifications are now met at the circuit level. Now we need to go and think about how am I going to do the layout for this PA. Now there are many ways you could approach the layout preparation for the PA. So one of the ways you can do matching network independently. For example, if you look at the uh, impedance matching network, if I prepare a layout, I could approach a layout which is isolated and from the output matching network side. So I can implement this in the one part of the PCB, leave out the metal space, and then similarly I can have the another layout which is for output matching network, and here is the layout section for the output matching network part. So you can keep these two as a separate piece, connect the ports or the pins wherever you want to connect the components later in order to prepare it for the co-simulation. And here you can see the Rogers material which I prepared. So this is the conductor, that's the via hole connecting the con to the cover plate of a 25 mil PCB on 3.66 dielectric constant. So using this design, we can go ahead and set up the EM simulation. And again, I already have detailed videos on how to perform momentum simulation. So I'm going to compute the EM performance over this PCB. The frequency range, I would like to start from 0, because remember this is the DC supply line. So the frequency should start from 0 for current DC current to pass. And I'm going to stop around the fifth harmonic or little higher than the fifth harmonic here. And then I will prepare a EM model so this will enable us to perform EM circuit co-simulation and also create the EM symbol, which basically is going to represent our design. So if you want, you can go ahead and generate a co-simulation symbol from the layout view, and that will represent your input as well as output matching network, and you can assemble the whole circuit together for validation. This is first approach. The second approach is I'm going to prepare a complete layout for the entire PA. So here you can see I have included the input matching network. I have included the output matching network. Now those straight long lines, I have also given some bend to minimize the size of the PCB, also both at the input side as well as the output side. And then I use the ground pouring, or what we call as inserting a ground plane, using insert plane option on the con layer, and you can define the desired amount of clearance, and you can draw a rectangle which basically will create this kind of clearance from your actual transmission line. And at the center, this is the placeholder where my device will get mounted, and I have pins placed everywhere for the schematic connection later. And also I have included enough via holes to do the ground stitching so that you have the right ground connection between your top layer and the bottom layer. Now, often when you work and you see some of these vendor PCBs like from Cree, you will notice these small, kind of pads. What are they going to do and how they are going to help you? Well, once you fabricate the PCB, let's say if you see performance degrading slightly, and if you need to increase the width a little bit or length a little bit in your transmission line, how do you do that? Well, in your layout, you can keep these kind of small rectangular blocks. And once your PCB gets fabricated, if you need to really, alter the width of this transmission line, you could go ahead and, take a copper ribbon, kind of things, and you can make this kind of connections to try to tune the performance of your PCB which you're testing. So that's how these small rectangle things which you see in the layout is going to help you. Similarly, there are some pads placed here which will allow you to play with the length of these open circuit stub on either side here. So that will give you some tuning flexibility after you have fabricated the PCB. And the short circuit stub, you can see this is again folded, and then immediately I have few via holes so that I can provide as nice a shorting potential as possible at that point of the stub. So with this complete PCB design, I went ahead and set up an EM simulation, produce the EM model for this design. And also if you look at the symbol, again, I went ahead not with the classical symbol, but you can always prepare either this kind of symbol or look-alike symbol to use in your schematic design. And that's what the fully integrated core simulation schematic along with the layout look-alike symbol can be seen here. So here is my input source connecting to this transmission line. And here are your SMT capacitors, resistors, transistor. So wherever you place the pins in your layout, you have this connection point allowing you to do this virtual PCB assembly on the schematic. And now rest of the setup is pretty similar. I'm still using these equations to do my computation. I have the variables for frequency, bias voltage, input power level, and I have the same two controllers running on this particular design. So let's go ahead and run this analysis here. So when we perform power sweep, you can notice gain has dropped slightly. In my schematic representation, I was getting 14.1 dB gain. With the EM simulation model, the gain is dropped by 0.4 dB. So I have 13.7 dB. And again, if I place my marker at the 3 dB compression, you can see now my compression has also shifted slightly on the downward side. And at the 3 dB compression point, if I place this marker to 29.8, I'm getting 40.5 dBm as the output power. Now, because the gain dropped, obviously the output power also dropped accordingly. But still, we are meeting all the specification which we are, intending to. And the efficiency at 3 dB compression point is 62%, and the drain efficiency is 67%. So the complete virtual PCB assembly level design is allowing us to meet all the specification which we are looking for. So if we go back at the agenda, what we set out to cover in part 2 video, so you can see we reached up to this point where we have all the required specification met by doing the EM circuit co-simulation, and we have a pretty decent looking layout for our PA design, which we can then proceed for fabrication by generating a Gerber file by going to File, Export, and selecting the file format as you required, such as Gerber, and prepare a Gerber file and load it for fabrication. So that's the end of part 2 video where we have a pretty good PA design. In the next tutorial video, we will look at how to perform a modulated signal analysis for our power amplifier, so that before we give it out for fabrication, we also note key things such as error vector magnitude, ACLR, CCDF for 5G NR specification, making sure this amplifier will work in the actual 5G base station or any kind of application you are looking for. Similarly, you can use your own modulated waveform, or even you can use your own custom I and Q waveform files to do your wireless or modulated validation. And after we look at the performance of our PA, we are going to talk about DPD and further linearize our design so that we can have much better performance in terms of spectral regrowth, and also improving the error vector magnitude, which originally would be around 5.6%, and we would like to minimize this to as low as possible to make sure we are again within the 5G specification limits. So that's all for this video. Thanks a lot for your time and attention, and hope you got some good information in this tutorial to apply that on your designs, and you would be able to design your PAs in a much easier manner with all the information shared. So thanks very much again, and wish you a very happy designing phase.